What is entropy? Well, entropy deals in the second and third law of thermodynamics. As stated by Marco E. Pavic, the entropy concept is frequently used in many scientific disciplines, including equilibrium and non-equilibrium thermodynamics, statistical mechanics, cosmology, life sciences, chemistry and biochemistry, geosciences, linguistics, social sciences, and information theory. The concept of entropy is used in many different sciences. The concept first came to be in the 19th century. The Carnots, Lazarus, and Soddy were onto something when they were thinking of how to improve the heat engines to be more efficient. Another man by the name of Clausius noticed the Carnots' work, and because of this, Clausius was the one to then explicitly state the second law of thermodynamics. He then summarized the first and stated the second law as, the energy of the universe is constant. The entropy of the universe tends to a maximum. The third law was discovered by Walter Nernst, saying there is an absolute zero of entropy where molecules are completely still. This is important because we now have a definite constant. So let's review how we understand the laws today. Entropy is part of the second law of thermodynamics as well as the third, and thermodynamics is a study of heat and other forms of energy and the relationships. The second law of thermodynamics of entropy states that the total entropy of an isolated system can never decrease over time. The entropy of the universe increases. The total entropy can remain constant in ideal cases where the system is in a steady state or is undergoing a reversible process. The third law of thermodynamics states that there is a definitive constant of zero for entropy that everything in regards to entropy is related to and is used as a reference point for it. There are different equations that relate to entropy. The equation for entropy is S equals K natural log W. Entropy, or S in particular, is a value that is used to quantize how kinetic energy can be dissipated in a system. We can relate entropy to microstates, or W, which is a value that illustrates the kinetic energy of a subject. Many different factors can influence microstates, which in turn would affect entropy. Something we can compare this to is a fish tank. In this small fish tank, it has a small volume and very few fish. It is considered to have few microstates, thus low entropy. In this large fish tank, there is plenty of fish and a larger volume. This would be considered to have many microstates, thus a large entropy. Another equation that uses entropy is S equals the initial of S plus the integral of Cp over T with a change in T. S is the same as the other equation. T is the integral of temperature, R is the temperature at which the entropy is found, Cp is the heat capacity, and SO is a constant absolute zero. What we will discuss now is the relationship between entropy and supercooling.
Supercooling is when a liquid goes past its freezing point but still remain in liquid states. This is caused by the purity of the liquid. According to the book titled Physics of Phase Transitions, Concept and Applications, most liquids do not crystallize in an absence of impurities if they enter the supercooled state. The supercooling limit is thus established by the homogeneous nucleations of the liquid. In these demonstrations, we will be using distilled water because distilled water will not have any impurity or the at least minimal amount for this experiment to work. Therefore, it will theoretically stay in the liquid states even when it goes past its freezing point. Because temperature is directly related to kinetic energy of the particles, and microstates is the quantized state describing the kinetic energy level of the system. Therefore, if the temperature decreases, so will the microstates of that system, which will also lower the entropy. In the next part, we will demonstrate how to find the entropy of a supercooled liquid in a closed system.
To find the entropy of the system, we can split it into the summation of three parts. The first part is the heating of the supercooled liquid from -10 degrees C to 0 degrees C, and it is found by taking the integral of the heat capacity of liquid over the temperature and dt. The second part is the freezing at the melting point temperature, which is -1.22 joules per gram K. The third part is the cooling of the supercooled water from -0 degrees C to -10 degrees C, which is found by taking the integral of the heat capacity of ice over the temperature and dt. The total entropy of the system was found to be -1.14 joules per gram K. The problem that was just done involved the entropy of a closed system. This obviously expands more than the single closed system to the surroundings and the universe. There is still much to understand and learn.